Hi.
Go on.
Transmitting power in DC or direct current can have great advantages over AC or alternating current.
Oh yeah, I did try to show you DC was better by electrocuting those animals. If it wasn't for that meddling Tesla and his stupid ways, now we would be living in a much better world of DC power lines.
Edison, you didn't know why AC was better back then and don't know why DC can be better now, so shut up! In fact, even I didn't know of these so-called high-voltage DC power lines until I heard this guy talk about them.
These cables are direct current cables, not alternating current.
Great Science Channel, check him out.
I was like, is this a joke or some special experiment? But then I did some in-depth research and realized that nope, it's real. Like I said in my previous video, Edison was transmitting 120 volt DC to homes from the source, which would mean huge currents through the transmission power lines. That would limit the transmission distance to a kilometer or two. The key success to Tesla's AC was that using transformers for the same power, he could easily bump up the AC voltage way high and in return drop the current way low. And that would minimize the power loss over the wire resistance for very long transmission distances. Then after the transmission, we would just drop it back down to 120 volt AC using transformers to distribute between homes as needed. If changing the DC voltage level was as easy as AC, we would just stick with DC. Why? Let me show you some of the benefits. Number one, every power line is equivalent to series resistors and inductors of the wire and parallel stray capacitors between the power lines or line to ground. The longer the power line is, the more of these components are added. Something like this inductor and capacitor. This is a filter. If I try to measure the AC output using my... The power line stray capacitors don't blow up like that. Let me just run it on low voltage AC. I have a 1 volt 10 kilohertz running through my inductor, and if I connect the capacitor to the output, you see that at this frequency the output is attenuated and phase shifted by 180 degrees. The impedance of the inductor grows by the increase of frequency, while for the capacitor it drops. So the inductor tries to block the AC while the capacitor tries to short it to ground. Same thing on the power lines. The AC gradually gets attenuated to a point that over a great distance almost no energy gets to the other side. But for DC, there is none of that impedance nonsense. At 0 Hz DC, the inductor impedance is 0 and the capacitor impedance is infinite. So all the current that goes in comes out of the other side untouched. Only the wire resistance wastes power, same as AC. That's why in AC power lines, they keep them well above ground and far apart to reduce those stray capacitances. But in some cases where we need to run the power under the salt water of the sea, say between United Kingdom and Europe, or underground in the cities, the line to earth capacitance becomes huge, sucking so much AC power because the wire is right beside earth or water. This will waste a lot of active and reactive power where DC doesn't have any problem whatsoever. Number two, DC only transmits active power and there is no reactive power unlike in AC. See, in an AC system, the total or apparent power is a complex number made of two components. The first one is real or active power in watts that actually does the work. The other part is reactive power, which doesn't do any work and is due to the inductances and capacitances in the circuit. Let me show you. Here I have my unloaded microwave transformer connected to 120 volt AC, and if I measure the current going in, it's around 5.5 amps, although I'm not powering anything from it. WTF? It's because I'm placing the transformer's primary inductor with around 22 ohm impedance on 120 volt AC, so it draws current. Here I'm also measuring the current using a shunt. The current in green looks a bit ugly due to the iron core. If you see here, the current and voltage are 90 degrees out of phase. Power is the product of voltage and current. When that product is positive, we have a positive power, which means that we are sucking power from the source. And when that product is negative, we have negative power, which means that we are pushing power back into the power lines. So in pure inductors and capacitors, where there is 90 degrees between voltage and current, the amount of positive and negative powers is equal, which means the net active power usage is 0 and we only have reactive power. Now, although the reactive power is not a waste, the current draw exists and wastes power over all the wire resistances. Imagine you have to send 2 amps to do something that only needs 1 amp. That's 4 times the power loss over wire resistance. My wires and transformer are getting warm as we speak with no output. Such nonsense doesn't exist in DC, where we only draw active power. Only the needed current is transmitted. Number 3 is the skin effect. As I've mentioned before, if you look at the cross-section of a wire for AC, the current is pushed to the surface of the conductor due to the electromagnetic fields. The higher the frequency, the thinner this skin becomes. This reduces the usable wire and increases its resistance and so more waste of power. But DC uses the entire cross-section, which means with the same wire we waste less and can transmit more power. Skin effect, line inductance and capacitance, and reactive power draw waste tons of power on AC transmission lines, where in high voltage DC we waste 30 to 40% less power. Number 4, DC lines are much easier to connect to each other unlike AC. Let's connect two AC lines together. Here I have my car inverter running on the 12 volt battery, and here I have the city power line. Both of them are exactly at 120 volt AC. And that's why you don't try that at home. Being 120 volt AC is not enough. See, the sine wave is coming from the city and the square wave is coming from the inverter. They are not the same shape and they are not in phase because their frequencies are slightly different. That creates huge voltage differences. To connect them, they must be the same shape, same frequency, same phase, same voltage level, same background, same ethnicity, and graduated from the same school. But for DC, we just need to make sure the voltage levels are the same. Right now, I have rectified the two sources with a diode and capacitor, and we can easily connect them together. Yes, we need to make sure they are the same voltage level and the same polarity, of course. And of course, if we connect them with diodes like this, it protects against reverse polarity and ensures that always the highest voltage will go to the output. So the voltage levels don't need to be the same either. So considering all these benefits, why don't we use DC all over the place? Well, I've already told you, it's much harder to convert DC for such superpower high voltage lines. At low voltages, converting DC is done very easily using the new circuits and transistors like the buck or boost switching converters. But imagine doing it at 10 kilovolt, 100 kilovolt or a million volts. In fact, I had to talk to one of my friends, Mike Piner, who's a senior electrical technician in a high voltage DC transmission station. You see Mike here in his natural habitat among the huge components needed to keep those super high voltage DC lines apart. He helped me understand how they convert such huge voltages. The bottom line is that, at least with the current technology, DC line conversion is more expensive and requires more maintenance compared to AC lines that use transformers, especially in urban areas that you need a power converter almost every block. Now let me show you how to convert AC into DC. Of course, you know that we can use a puny single diode rectifier, and I'm using a light bulb as the load. And on the scope you can see that the yellow line is the input sine wave and the blue is the output of the diode, where the negative of the input is cut off. Now to make it a DC, all we need to do is to connect the capacitor across the load. Always pick a properly rated capacitor for your voltages. Now if I connect it in, you see that the light goes brighter as the capacitor is helping to keep the voltage up, discharging between the pulses and charging with the next positive peak coming in. The capacitor here is doing a lot of filtering because the AC component here is pretty large. We could also use a full bridge rectifier instead. I'm using a differential probe here to measure the output because the input and output reference voltages are different here. And you see that the bridge is also flipping the negative wave of the input up and using it, and that's why the light is at full brightness. Now if I connect the capacitor, you see that the light goes even brighter and the ripple voltage is much smaller because the peaks are coming at double the frequency and the voltage doesn't have time to drop too far. Now imagine if we had 3 phases. So I have to make my own 3 phases. I had made this contraption before where I'm using a brushless DC motor to turn another one as a generator. These motors work with 3 phases coming in to turn a permanent magnet, and in reverse, if you turn them, they generate 3-phase output. Here we are. If I run the motor, we get 3 phases coming out of the other end. The reference point of the 3 phases is the center of the resistors between the phases. Now we can use a 3-phase, even fuller bridge rectifier, or EFBR. Every phase being more positive than the other phases feeds the positive line through the top diodes, or being more negative than the other phases gets fed from the negative line through the bottom diodes. Okay, I have my EFBR hooked up to my 3 phases. Let's turn it on. See? The blue is the output measured by the differential probe. Because my voltage levels are smaller, the effect of the diode drop is more significant. Let me turn off the 3-phase voltages. The fascinating thing is that now I have 6 positive waves per cycle that add up and create my output, which is already pretty DC looking without a capacitor. Now the AC component is much smaller and higher frequency and easy to filter when I connect my capacitor. In those high voltage DC centers, they kind of do the same thing. First off, there needs to be 3 phases coming in. Then they use a transformer to bump them super high to 100 kilovolt, 250 kilovolt or more. They also use another transformer to shift those 3 phases 30 degrees to create 6-phase AC. Then they rectify these 6 phases using the mother of all fullest bridge rectifier, or MAFBR. Also, instead of diodes, they use something called silicon controlled rectifier, which they also call valves they can open and close. These SCRs are like diodes that can be turned on using an external signal when the voltage across them is positive. Imagine these components have to be huge so they can withstand 1,000,000 volts and carry tons of current. Rectifying 6 phases, they get a huge DC voltage with a smaller ripple voltage at 12 times the main power frequency. Much easier to filter. And yet, they have to put huge capacitors and inductors size of a building to be able to handle the super high voltage and current. Wow, that power plant is like my mecca. I could ride those rectifiers forever. Too bad they won't let me in due to liability issues. A bunch of kittens. Anyway, of course there will be a bunch of power loss converting AC to high voltage DC, but then you can transfer it much more efficiently over continents until it reaches the next station where you have to convert it back down to AC to distribute. They use the same kind of valve circuit and setup to switch the DC back into AC and through a transformer and filter to create the 3-phase output. Of course, the created 3 phases have to be synchronized with the existing power system, otherwise explosion. That's why they use the existing 3 phases to time and switch those huge valves to make perfect signals. Let me show you how to create AC from DC. Here I have 2 switches that are controlled by the same signal and switch the DC input to the AC output. If the switches are up, they send the forward voltage out, and if they switch down, they send the reverse voltage out. So if it switches back and forth, it creates an AC at the output. Here I made the circuit with a dual pole dual throw switch, and if I switch it, I can create AC. And if I make 2 more of these and switch them 120 degrees out of phase, I can make 3-phase signals and filter them into a nice sine wave. Now we just need to hire a bunch of underpaid workers to switch these at 60 Hz. High voltage DC lines are currently used for backbone power transmission only, but maybe in the future the technology lowers the cost and increases the reliability of DC conversion so that we can use DC all over the place.
As I always intended.
Get out!